So the next topic that we are going to deal with is the steady state output noise variance due to quantization error signal. Now, this problem or the kind of theory behind this can be understood only by looking into the problem also. So I'll just initially explain the theoretical concept and then we'll look into the problem. The problem is attached as part of this PDF itself, so you can look at it at a later point of time also. Okay, so we are going to begin with the topic steady state output noise variance due to quantization error signal. So we are going to consider this point out here. So we have a LTI system with unquantized input. So that will be given by this diagram X of n. You have a system H of n which gives the output Y of n. And with a quantized input, it would mean that X of n is the input in here. And you have a error signal that comes in which is due to the quantization, and along with that you get the output as xq of n, which is the quantized input, and that is fed into the system. So naturally, since the input here is x of n and here the actual input is xq of n, there will be a difference in the output which will be given by y dash of n. So y dash of n, as per the convolution property or the system nature of the system, y dash of n will be given by xq of n convolution h of n. So xq of n is actually x of n plus e of n convolution h of n. So when we split this, we get it as x of n convolution h of n plus e of n convolution h of n, and y dash of n can be deduced as y of n, which is actually the original output y of n plus e of n, which will be attributed to the error that is entering into the system and which will be convolved with this impulse response h of n. So this variance of the signal, that means this e of n factor will be called as a variance of the signal, and that is what we are going to determine over here. So we have a defined formula for this. So the steady state output noise power due to input quantization error will be given by this formula. So it will be sigma EOI square equal to sigma E square summation of n equal to 0 to infinity h square of n. And moving on further, it will be integrated or explained in terms of surface integral, and which is given by this equation over here. And as we move further, we have this particular representation where sigma square EOI is equal to sigma E square into 1 by 2 pi j contour integral or the surface integral h of z into h of z raised to minus 1 z raised to minus 1 d of z. Now this will be given by the another alternate form where you have summation n equal to 1 to capital N residue of h of z into h of z raised to minus 1 z raised to minus 1, where z is equal to pi, and this will be solved as a later part of the equation. Now we'll move on to the problem, and this problem will be, first problem we'll look into will be 8.11. If 8.11 is clear, naturally you can understand 8.12 and 8.13. So we take a look at this problem 8.11. So here the question is as follows: for the recursive filter shown in figure 1, the input x of n has a peak value of 10 volt represented by 6 bits, and we are asked to compute the variance of the output due to A bar D conversion process. And this is a diagram given for the system. So if you look over here, you have the x of n, you have the error that is crept in, and you have the feedback over here. This is said to be recursive filter, which means there will be a feedback from the output. So this is definitely the output side of it. So this is y of n, then this point will be y of n minus 1. So as we move along, we can see that in R, we assume that the step input is input is positive. So the 6 bits are used to represent only the positive numbers. So that is the assumption taken over here. So we have this the quantization step size, which will be defined as follows: Q will be equal to R by 2 raised to B. So here R is 10. Now it is because of the fact that this having a peak value of 10 volt, which means R will be equal to 10. So that can be defined as follows, and then B will be equal to 6. So moving on, Q will be equal to 10 by 2 raised to 6, the usual formula that we have learned, which will give you the value of Q. Now then the variance of the error signal, that is sigma E square, will be equal to Q square by 12. This is also the formula that we had derived earlier. So it will be equal to 0.15625 whole square by 12, which will give you this value. Now we have to consider the output of the system. So when we consider the output of the system, your y of n will be equal to 0.93 y of n minus 1 plus x of n. So when we take the z transform, we get y of z is equal to 0.93 z raised to minus 1 y of z plus x of z. So this equation here, how does this equation come about? We can understand it from this signal flow graph. So y of n, as I told you earlier, it is a recursive filter. So that means a feedback goes from the output. So this will correspond to y of n minus 1 and it goes over here. So we can say that y of n will be equal to x of n, that comes over here, plus y of n minus 1 into 0.93. That is the one given by this equation. So when we take this z transform, we get it as follows. And moving on, this will give you the transfer function of the system. So y of z, we'll bring it to the one side and we'll take the ratio of y of z by x of z, which will be equal to 1 by 1 minus 0.93 z inverse, which is the transfer function of the system, and we'll get it in this particular format. Now to evaluate this particular thing, we need to implement this particular formula that we had already looked into. That is we have to implement this particular formula. So out of this thing, we know sigma E square and we know h of z. So now we have to determine the other factors which will be helpful in the computation of this steady state output noise power. So moving on, we have the term h of z that is defined out over here. So we need to evaluate h of z into h of z raised to minus 1 into z raised to minus 1. So all you need to do for determining this term is replace z with z raised to minus 1. So this will become z itself, and this will become z raised to minus 1. So this will be 1 by 1 minus 0.93 z inverse into 1 by 1 minus 0.93 z into z raised to minus 1. So when we compute this particular operation, we get the final equation, that is for h of z into z of z raised to minus 1 into z raised to minus 1 will be this equation. Now from this equation, we can realize that the poles of this particular equation are 0.93 and 1.0753. So as we see over here, the poles that are available here in this particular equation of h of z raised to minus 1 into z raised to minus 1 are P1 equal to 0.93 and P2 equal to 1.0753. Now for our concern, we will be considering only the poles that are inside the unit circle in z plane. So we have only one valid pole, that is P1, which is equal to 0.93. So the output noise power due to this A bar D process will be given as sigma square EOI equal to sigma E square. We have this contour formula out over here. But to realize this, this will be equal to sigma E square summation of I equal to 1 to n. Now what does this n mean? N is representing the total number of poles inside the unit circle. So here out of the two poles, we have only one which is equal, less than 1 or equal or within the unit circle. So here n will be equal to 1. So which is why we have only one set of equation. So that will be equal to Pi, where z is equal to Pi. That is not Pi, actually P, only one set of pole will be there. It is actually Pi. But this Pi can range from 1 to n, where n is the total number of poles inside the unit circle. But for our concern, we have only one pole which is lying inside the unit circle, so that n will be equal to 1. So this will be equal to sigma E square into z minus 0.93 into 1 minus 1.0753 by z minus 0.93 into z minus of 1.0753, where z is equal to 0.93. Ultimately, when we substitute all these values, we get sigma square EOI, which is equal to 0.0151. Now this particular problem will have its own variance in the form of 8.12 and 8.13, which can be understood after a deep study of the first problem, and it will be easy to solve.